we want to look at two key concentrations of oxygen down here, which are sort of the key things that are happening in the body, being these two. Because at 100 millimeters of mercury of oxygen, that's what the hemoglobin is approximately exposed to, and when it's picking up oxygen, so the alveoli. 40 is approximately the concentration of oxygen within sort of, resting tissue, which of course just means all tissues are, all cells are metabolically active. I mean, they're using up oxygen and getting CO2, but this is sort of a, where it's not, more active than that. And so, really, again, when we're doing this, it is easier to sort of, to look at, read it Hebrew style. It doesn't really matter, but the idea is what's happening here and what's happening there, and why is it shaped that way? Like those two bullet points are what I'm questioning on. And basically, this is obviously the plateau phase. What is actually happening there biologically in our body?
Loading up.
We're loading up with oxygen because that's where the hemoglobin is passing through. We did those steps. It's being exposed to that much oxygen, and we can see it's basically becoming fully saturated, or almost fully saturated. That's how efficient we are. So that's why we call this the loading phase. It's loading with oxygen. And the other aspect is, from a biological significance, what is sort of the advantage biologically of having a plateau, versus having it sort of a linear relationship or something like that?
Efficiently loading up even at like high altitudes.
Yes. Again, I have a hard time getting that in one sentence in a way, like very efficiently, but of saying it. But the idea that from a biological standpoint, what's nice for us is that even if you aren't getting that much oxygen in your alveoli, high altitude, or what if you have some sort of blockage or something where you're just not getting enough oxygen? We don't want the hemoglobin to just become 50% saturated. Because it works this way, it still is nearly 100% saturated. And that's very good for us, right? That's obviously a survival advantage. And so that's sort of the, again, the biological significance of why it's a plateau, which is all we're worried about here. Those are the two things. It's loading with oxygen, and it's a plateau to allow that efficiency at lower oxygen concentration. Remember, no essay questions anyway involving this. The second part is we have the steep phase. Again, what is basically happening here? It's loading the oxygen to the tissues, because we don't want this hemoglobin just to hang on to all of it and just say, like, let's go back to the lungs. Its job was to deliver oxygen to the tissues as needed. And you can see, again, at our little level of the resting cell, if I drew it right, it's about 75% saturated. And again, to me, that means it released about 25%, right?
Resting.
To a resting cell. Now, the advantage of it being, why doesn't it just stay a plateau? Well, if we're more metabolically active, we want it to release more oxygen. We want this to be responsive to the needs of the tissue. The more oxygen we need, the more metabolically active. We've been playing this already. That's the lower oxygen we have. We want it to give the oxygen. That's what it's there for. It's going to start, decreasing saturation, which means releasing more and more oxygen. So again, in summary, this part of the curve represents the unloading phase, because that's where hemoglobin is unloading some of its oxygen to the tissues, and it's steep. The biological significance of that is now it's responsive to the needs of the tissue. The more oxygen it needs, the less it hangs on to, the more it gives up. So the only other things then are the shifts. And again, the easy way, you can memorize shifts all you want, and that's fine. But for me, the sort of two factors make it easier. You have a shift to the right, and I guess I'll use a different color. The hemoglobin can behave differently under different conditions, and shift to the left of normal, to the right and the left of normal, of the standard conditions. And so, to really, again, there's 5 curves that we need to know, and to sort of set, or at least in my mind, again, you already know sort of how I've done it. A shift to the right You just have to realize it's what?
Releasing oxygen.
It's releasing more oxygen. And, you know, again, biochemistry part saying it's less affinity means it's releasing more under those conditions. So a shift to the right means it's going to, you know, under each one of these sort of, you know, levels here, it's going to end up releasing more O2. Again, the hemoglobin has, you know, less affinity for the oxygen. Okay, so the key with that is that, again, just when you're thinking biological significance, this should make sense. And that's sort of why, you know, physiology ultimately is common sense. We're here, it makes sense, we're trying to restore homeostasis, and so it should work out unless something's gone foul, okay? So if you think, anytime you think, any condition that you relate to that we need more oxygen, it's going to represent the shift to the right. And an easy way to do that is to think metabolism, you know, or exercise, or whatever you want. It's not the only conditions that can do this, but again, we do this now, we're very used to this relationship now, that if you're under higher metabolism,
low oxygen,
high CO2, okay, temperature-wise,
up,
higher temperature, and CO2, I don't know if I put it up here again yet, see, but we will again. If we can put it up there, we'll be reviewing that next. CO2H2O. We keep seeing this come up. The CH2 levels are related to what? pH.
mm-hmm.
Okay? And as CO2 goes up, therefore, hydrogen goes up, and therefore pH goes down. So, if we are correct, okay, and now this makes sense to us, right? I mean, that's pretty straightforward for us now. That means higher metabolism. Well, higher metabolism, you know, do you want the hemoglobin to release more oxygen?
Yes.
So therefore, it should shift to the
Right.
okay. So we're suggesting this will cause a shift to the right. And you know what? It does. So if you look at, again, I'm not using the PowerPoint today. If you look at all three of those, higher CO2, higher temperature, lower pH, they all represent a shift to the right. Again, hemoglobin, we already know now from the other part, you know, when carbon dioxide starts building up, it binds to a different side of hemoglobin, changes its shape, allows it to release oxygen more. pH, we saw this in carbon dioxide transport too. Hemoglobin can bind hydrogen, acts as a buffer. When hydrogen is being released, hemoglobin binds, changes shape, allows it to release more oxygen. Temperature changes shape of, you know, enzymes and proteins, right? Changes its shape, allows it to release more oxygen. If we had hypothermia, which way would it shift? To the left. If we had low CO2, okay, you know, high pH, yeah, okay. Am I going to have at least one shift to the left?
Yes.
Yes, thank you. Okay, those are 3 of the 5. Okay, the fourth one to stay consistent is, let's say again, you know, you get this idea of maybe, you know, high altitude,
shift to the right.
or really when it comes down to it, other conditions in which you basically, you know, high altitude is fine just for our purposes here, in which you really are not getting the same levels of oxygen.
Nope.
So let's say not getting enough, it's really little. Maybe that's not a perfect way to say it, O2. So first of all, if you're not getting enough O2, you're high altitude, you want it to shift to the right, okay? Obviously that makes sense, and it's going to. The reason, the way it's going to work though is, if you're not getting enough oxygen to do that aerobic respiration, you're going to be doing glycolysis. And in this class we didn't go through all the steps. This is anaerobic respiration. This is when you're sprinting, you're building up, you know, lactic acid, that kind of thing. For most of us, we have that idea. So if we're doing that, because we don't have enough oxygen, that's good. It's getting us some ATP. But the idea is, well, we don't want hemoglobin to hang on as tight. And so one of the intermediates, which you can just know is 2,3-DPG of glycolysis, not only does its thing in glycolysis, it actually binds hemoglobin. This is why I like hemoglobin now. It's very multifunctional. It binds 2,3-DPG, and it causes, again, a shift to the right. And that's why 4 of the 5 curves, you know, again, they all shift to the left at the opposite, but 4 of the 5 curves make sense to us in the sense that when we need more oxygen, that's why this is the key to me, you shift to the right. And you know, we've already demonstrated that it really is releasing more oxygen. So that the shift to the right means it's releasing more oxygen. All these conditions, which are the 4 of the 5 curves, would be conditions in which we need more oxygen. So it should make sense to us. Doesn't. So remember, not an essay, you're not drawing this. I'm literally giving you a curve. I'm going to give you a graph like this with the 3 curves, and I'll ask questions about it. Okay? The 5th one, fetal hemoglobin compared to maternal is shifted to the left. And without going into, you know, again, it's not an essay type thing. The idea is that this matches, again, the summary of it, it matches the fetal environment, right? Fetal's not exposed to that much oxygen. It's basically loading up under these conditions. It's unloading to its cells under those, and so it works out perfectly for it. So it's shifted to the left, A, and the Y, you know, here we're talking about things binding to our hemoglobin, causing it to change shape and the shift. What's causing the fetal hemoglobin to be shifted to the left?
Gamma chains.
Mm-hmm.
It has 2 gamma, so fetal hemoglobin has 2 gamma instead of the beta. Okay? They both have 2 alpha. So hemoglobin again consists of 4 chains. Our adult hemoglobin 2 alpha, 2 beta. The fetal hemoglobin 2 alpha and 2 gamma. Once you're born, you have to get rid of all of that gamma, you know, all that hemoglobin actually, not just the chains, and replace it with adult hemoglobin, and that's why you can build up bilirubin and have a newborn with jaundice. Those are the 5 curves. So as long as you understand this, you should be able to answer those questions. Just remember, I'm going to have shifts to the left too, which are the opposite. As long as you know what shift to the right, you can always shift to the left. Okay, carbon dioxide transport, you've got the list of steps. Not a lot of, you know, oxygen transport, carbon dioxide transport, very straightforward questions. Not essay, I'm already telling you that, but you just have to know them. So that's pretty easy. This is the hardest part. This equation, by the way, so we talked, the last thing in the chapter, and then we can play the kidney game. The last thing in the chapter talked about control of respiration. Now we already had an idea when respiration was go up or down, but really we looked at control, we were looking at, the body's looking at oxygen gas, CO2 levels, and corresponding hydrogen levels. A buildup of CO2 is called hypercapnia. And again, hypercapnia, again, because of the idea that we can acidify the blood, and that causes bad things. So we have peripheral and central chemoreceptors. Okay? Where are the peripheral ones? Where are the baroreceptors? Carotid and aortic. Where are the peripheral ones? Same place. Now, the main thing of that is they respond mainly, because we're looking at these 3 things, peripheral mainly respond to low O2. Okay? They respond to all 3 of these, but low O2. But which one is more critical as far as building up? Not having enough oxygen come in or too much CO2?
Too much CO2.
The immediate is CO2, because look what we have here. Look at this buffer here. Okay? We only release 25% of these conditions. We can release more and more. We have the hemoglobin, can get us by a little bit. But CO2 is going to acidify our proteins and basically cause us some bad things here. So the central chemoreceptors, and this equation, which now we've seen 3 different times in this section, why I did this at the beginning, why it's so important is the cerebral spinal fluid has this enzyme, this equation happens, so that CO2 diffuses across the blood-brain barrier. We have this reaction, and this basically is what this chemoreceptor responds to. Bottom line is that the central chemoreceptors are responding mainly to, which are related obviously, to CO2 and hydrogen levels. The peripheral ones, the oxygen levels. And that's the only thing you have to know about the control of respiration. give you one other thing, and then we'll play the kidney game. Because the other thing, we'll keep that there, that in that chapter, again, remember you have to do the gas laws, I've already said that, the things you've just done, we've already reviewed that, number 17. Hypoxia. Remember that chart that I basically said you do have to know the different types of hypoxia, and we sort of kind of drew something here. This would be the alveoli. This is the red blood cell. This represents the circulatory system. There's our heart. And finally, we're getting oxygen to the tissues, which are the cells, and really to the mitochondria. Of it. And so basically, if you're not getting enough oxygen, that's workable within these cells, you have hypoxia. Okay? Not enough oxygen delivery to the cells and usable. But there are 4 different types, at least as described here. And I sort of like it because it's sort of, you can actually put this in this kind of figure here. And so the first one was, you have oxygen. You're not getting enough oxygen actually into the blood. You're not getting, perfusion is basically what it is, right? Getting it from the alveoli to the blood, or there's not enough oxygen there. The bottom line is you have low arterial O2. And what was that called?
Hypoxic hypoxia.
So, yeah, that's like weird, right? But hypoxic hypoxia. It could be, you're not having enough oxygen. Okay, you're climbing the Everest. It could be you have COPD or something, else in which you're just not able to get enough oxygen in, or even restricted. So that, bottom line, low O2 coming in. Hypoxic hypoxia. You're hypoventilating. Second one though, let's say that works okay, but you don't have enough red blood cells or functional hemoglobin, because it's a combination of those. Any of those combinations are called anemia. So this is anemic hypoxia. Because obviously, if you can't, we already see how important that is. Your hemoglobin isn't, or we don't have enough, or it's not functional, we're not going to get enough oxygen to the tissues. So that's anemic hypoxia. Okay, let's say all that's good. We get it in, plenty of blood, plenty of hemoglobin, but we have compromised circulation, cardiovascular problems, etc. And so we're not delivering, okay, we've got plenty of oxygen here, it's doing its job, but we're not able to deliver it effectively to the tissues. Ischemic hypoxia. Finally, we get it there, but it can't be used by the cells. We poison the cells, basically. Cyanide's an example. It's toxic. So know that. Okay? So, not too bad. Easy for me to say. But, 17, 18, that's pretty much what a good summary of the major things. Any questions? Any other questions on 17, 18? Okay. For 1920, okay, let's do 1920. Let's go in order. Just do some. Because 19, there's not a lot. I want to make sure we sort of know what we need to know on that. Because to some extent, I wasn't sure I was going to get my voice back, but I seem to have it. So, the basic idea of chapter 19 was to introduce us to sort of the kidney and the different parts, if you're not used to knowing the names, and the blood supply, and mainly as far as details, which we'll talk about now, it's really filtration. Okay, the forces of filtration and the local controls of filtration. That's sort of the major things. And then for the proximal tubule, again, proximal tubule to us means
Low
low reabsorption. And when it comes down to it, that's pretty much what I want us to know from it. Even though I go through the steps, sodium, and then that drives the negative, and that drives the water, which is cool, I'm not going to waste time sort of, worrying about that, because C chapter 20 is our big boy. So just that most of the water, most of the salts, some of the urea, and all of the what? What should be reabsorbed here? All of it. Glucose and
Amino acids.
amino acids. They're going to use transporters. That will effectively transport 100%. If you have high blood glucose, higher than normal because of diabetes or some other condition, these become saturated. You end up with glucose in your urine, which is called glucosuria.
Glucosuria.
And of course, what's following that glucose? Water. That's why you urinate a lot and are thirsty, because basically, you could just see now, you see the overall concept, why I'm hot on that from the beginning too. Basically, water follows, an important part of our homeostasis, and when things go wrong, it follows salts, it follows sugar, it follows our proteins, which we'll do again. They're attracted to proteins. And that determines a lot of, our water homeostasis. Okay? But going back to this then. For filtration, basically, again, let's put the blood supply. How many liters a day go through our kidneys? 180 liters. How many times circulation is that?
60.
60 times our whole blood supply circulating. And the key is, at any given time, 25% of our cardiac output's going through, but we don't want all of it to go through at once, or else blood pressure drops. And we actually control this filtration rate, which is GFR, pretty tightly here, with blood pressure. And so we're going to do that in a minute. What do I want to say first? Okay, one thing I want to say first. Well, I guess just that, again, we're going to really deal with control with these afferent arterioles. The efferent, we're not going to really talk about much. Then we have the peritubular capillaries. So we have the efferent, we know the glomerulus. I get it, oh yeah, now I want to say. For filtration, the first thing we want to know is basically what gets in. The easiest thing is to think of what doesn't.
Proteins and cells.
Proteins and cells. There might be a few other things, but that's really the key. We're going to normally make a protein and cell-free filter. Most of it we're going to take right back. Okay? It's worth it to have this high flow and control of everything else that we've discovered in chapter 20 and more. All right, fine. We want to control GFR just like we want to control blood flow into tissues. And when we think about that now, the first thing to think about there are three forces that control GFR. One force is sort of, let's say, pushing the blood
Hydrostatic
filtering
pressure.
in, and then there's two forces which help
osmotic
oppose that,
pressure.
and then we have a net balance of flow, which is GFR. So the pressure which is pushing it in is the,
Hydrostatic pressure.
okay, that's basically the blood pressure within the glomerulus. It's not the systemic blood pressure, because we're going to control that, right? We're controlling the flow here. But it's the actual pressure of the glomerulus, the pressure within those capillaries. Remember, the overall idea of filtration was that it was basically pores. And so big things can't get in, but that means little things can, and we're pushing it through holes. So that's pushing it in, okay? But we have two opposing forces that are sort of keeping it at a certain amount. One of these is the fluid pressure, which is just that there's fluid in here, right? So that pushes against it. But the other one was,
Osmotic.
okay? Proteins are out here, they're not in here. That's called colloid osmotic pressure. It's helping opposing this force by the water being attracted to stay with the proteins, okay? But there's a net flow, and that's GFR. Okay, that will basically be it. Again, if you use my famous example of liver failure, and we're asking GFR, you want to always think about the steps because the answers might be in the middle of the steps, even though you might see GFR in the answer, you might see other things. And so you basically go, okay, we're talking about this system here, and so liver failure would affect what? The rectal.
Colloid osmotic pressure.
And right before that, proteins.
Proteins.
Because if you see hypo or hyperproteinemia, you've got to deal with it, right? So it would be hypoproteinemia. And then you think exactly like you did. That's related to one of these pressures, which is?
Colloid osmotic
And it's
pressure
doing what to it?
decreases it.
You're like, yeah, less is basically being drawn out, so it's decreasing colloid osmotic pressure, and therefore
GFR increases.
GFR increases. Okay? And again, you can kind of, as long as you're not giving clues to each other, you could be out there like doing this and this, you know. People are in their mind doing it, as long as we're not looking at the other person while we're doing it, right? So, anyway, that's that. Any questions about that? I mean, people are doing this stuff all the time. You know, holding your breath, hyperventilation. All right. So, the only other major thing here, and then we do chapter 20 and we do the big boys here, is the two local controls. I don't care about systemic controls. I'm not going to test that. I'm not going to test clearance, even though we talked about it at the end. I'm just talking, the last two things are this. We have, you know, basically what was, you know, we want to control GFR. We had two local controls. One of them just had to do with blood pressure and how it affects these afferent arterioles. And this is related to something we just talked about before, because the afferent arterioles are made of smooth muscle, or what constricts and contracts, just like the systemic ones that we were talking about. And so if blood pressure is increasing, if we have an increase of blood pressure entering this, we don't want that to cause a GFR increase. What are these afferents going to do?
Constrict.
Constrict. That's the myogenic response. It's like before we called it, you know, myogenic autoregulation. It's just how smooth muscles work. Okay? But that's good. So blood pressure is increasing, and if you remember that figure, basically, you know, you can have blood pressure increase a great amount before GFR increases. So this is a pretty effective system. Only afferent. We're not dealing with efferent at all. Okay, that's one, myogenic response. The other one has to do that this ascending loop of Henle isn't over here, is it? This ascending loop of Henle is passing right in between the afferent and efferent arterioles, and it's helping to control GFR. And right out here, surrounding this, which is part of the player, are these granular cells. Okay? And the sensor, I'll put here and put it there too, are going to be cells of the ascending loop called macula densa. And so it's going through there, but right now, just to look at it, if GFR is increasing, and we're flowing through here, it's measuring the flow of